What's the angle between these two lines? It looks about 45 degrees. Well, it looks like it, but is it? Actually, you're seeing these two lines through a television camera, and the camera never lies, or does it? Well, here are the two lines that we've been looking at, and you can see that as I vary the lines, they change. In fact, it's more like a right angle. We got the effect of being more acute because the camera was looking at the lines obliquely. As I move the lines, I transform the angle in your picture. So this effect actually is well known. It's called perspective, and artists have known about it for a long time. Now, the mathematical study of perspective is called projective geometry. Any geometry is just the study of properties which are preserved under transformations. And the transformations of projective geometry are just those which correspond to taking pictures. Well, if you've only been used to ordinary Euclidean geometry, this may seem rather strange, because the sort of theorems that we get in projective geometry will not change if we look at the plane from a different perspective. For example, this theorem. This theorem will still remain true no matter what perspective we view the plane from. So what are the sort of theorems that we can get in projective geometry? Well, as we've just seen, we're not going to be able to use angles, because angles change as we change perspective. So in fact, angles are out. Now, what about distance? Well, what about the length of a line? Does that change? Well, actually, by looking at this line, you can't really see what length it is. In fact, it turns out that it's really quite a small line. So, in fact, lengths have to be out as well. Well, that's not too good. What about the equality of two lengths? Will that remain the same if we vary the perspective? Well, let's see. Here, the central point looks as if it's just equidistant from the two other points. But actually, this is also a trick of perspective, because if I actually were to measure the distance, I think this is about 30 centimeters and this is about 20 centimeters, so it's not really equidistant. So in fact, they're not the same length, and in general, the ratio of lengths will not be preserved in projective geometry. Now, what about geometrical figures like circles, for example? Well, what distinguishes a circle is that all the diameters are the same length. And you guess if length isn't preserved, then circles won't be preserved either. So circles won't play much of a role in projective geometry. In fact, we can illustrate that. Here we have a picture of a circle, and you see that as I change the perspective from which you view it, then it slowly changes into another geometrical figure. In this case, what we get is an ellipse. Well, we're not doing very well in our list of the properties that are preserved under projective transformations. I mean, will we get any theorems at all? Well, of course, we've already seen an example of a theorem that we get, so there must be certain properties that are preserved in projective geometry. And they're rather basic properties. The most basic property or thing of all in geometry is a point. Now, if you look at a point, no matter from what angle you look at it, from what perspective, you'll always get a point. So the property of being a point is certainly preserved under perspectivity, under projective transformations in projective geometry. What about straight lines? No matter how you look at a straight line, it will still remain a straight line. So the property of being a straight line is also preserved. Then there's another property which is somewhat related and a little bit more subtle, and it's this. Supposing I have a point lying in a straight line, then no matter how I look at this point on the straight line, it will always remain a point on a straight line. Now that property is called incidence, and so we've seen that incidence is preserved in this projective geometry. So at least we have some basic properties which are preserved in projective geometry, and to study mathematically what projective geometry is about, we must study the sort of mathematical results we get from looking at these three basic properties.
We're going to take two really simple statements and see what sort of interpretation we can give them in projective geometry. Here's the first one. Given any 2 points, there's a unique straight line which passes through both of them. So 2 points determine a line. Well, let's change our perspective of that by moving the camera around. whichever angle we choose to look at it, it's still true that we have 2 points and a straight line passing through both of them. And that's because the only properties we're using are preserved. Points stay as points, lines stay as lines, and incidence is preserved. So in projective geometry, 2 points determine a line. What about the second statement? Given any 2 lines, then there's a unique point which lies on both of them. Well, again, let's change our perspective and move the camera. Whichever angle we use, it's still true that we have the 2 lines and the unique point. So in projective geometry, 2 lines determine a point. But now, just a minute, there's something not quite right with this statement. Do any 2 lines determine a point? What happens if the lines are parallel? Well, it so happens that I've got a couple of parallel lines drawn on this bench here in the studio. And the whole nature of parallel lines is that they don't meet. So in this case, 2 lines don't determine a point. But what about the view through this camera? You see, the lines do appear to meet at this point. Let's just concentrate on the lines, and you see that on your screen there are just 2 lines which meet at a point. And yet we get that by taking a picture of 2 parallel lines, 2 lines which we know don't meet. So we seem to have got a point from nowhere. And that's a problem, because it violates our principle that points are preserved. If we want to keep this principle that points are preserved, then we have to say that parallel lines meet. And since they can't meet at any ordinary point on the plane, we have to introduce some new points. It's like saying that parallel lines meet at infinity. We have to add in some points at infinity. And we call them ideal points, just to make quite clear that they're not in the ordinary plane. Well, if we think of these lines as being in the projective plane, then they meet at an ideal point. And this point on the screen is a picture of the ideal point. Let's see if we can find out some more about ideal points. We'll show you a plan view of what's happening at the same time, so that you can compare the original with the view through the camera. Let's take a third line parallel to the first 2. You see, it appears to pass through the same ideal point. And in fact, any line parallel with these will also appear to pass through the same ideal point. What about a different line? Well, that doesn't pass through the ideal point, and that's just as well, because it already meets one of the lines in a real point, and we don't want it to meet it twice. What about another line parallel to this oblique one? We haven't drawn all of it in just to avoid confusing the picture. But I think you can see that it meets the other oblique line at a new ideal point. And any other line parallel to these 2 will also appear to meet them at an ideal point. Well, I think you can see what's happening. For each new direction, we'll get a new ideal point. And more important, all the ideal points lie on a straight line. We call it the ideal line because it consists entirely of ideal points. So, as well as all the new ideal points, we also get one new line. Well, that's all very well, but the whole reason for introducing these new ideal points was so that these 2 statements would be true. And now we've found that all the ideal points lie on a line, a new line, we'd better check that they're still true. The first one, 2 points determine a line. If I have 2 real points, then they determine a real line. 1 real point and 1 ideal point, and I get the line through the real point in the direction of the ideal point. And of course, if I have 2 ideal points, then they determine the ideal line. So in projective geometry, 2 points determine a line. What about the second statement? If I have 2 oblique lines, then they determine an ordinary point. 2 parallel lines determine an ideal point, and 1 real line and the ideal line determine an ideal point. So, once again, in projective geometry, 2 lines determine a point. There's no special case. Well, just to be clear about the context, we have a new notation. we use capital letters for points and lines, so that while this statement as it stands is technically incorrect, if I make it clear that I mean projective lines with a capital L and projective point, capital P, then it's true without any exception. And now we've seen all about points and lines, we can go on to study some of the theorems of projective geometry.
Well, what are these theorems? We're going to take as an example the theorem that I mentioned at the beginning of the program. Take any triangle, take any other point not on the three lines. Now join each vertex of the triangle to this new point and continue until you meet the opposite side. The three new points make a new triangle inside the old one. Now extend the corresponding sides of the triangles in pairs until they meet. Now, when you've done this 3 times, you actually get 3 points. And what the theorem says is that these 3 points actually all lie on a straight line. Well, that actually is quite a surprising theorem. If you find it surprising, the best thing you can do is to try and do it for yourself. That's the only way to understand a theorem in mathematics. Do it for yourself. So I'll try and do it for myself here on a piece of paper. I've got a triangle and I'm given a point inside, and the construction tells me I've got to take the line from each vertex to the opposite side. When I do that, I get 3 lines. And now these give me 3 points on the opposite sides, which I join up to form a new inscribed triangle. Now the theorem says I must actually extend the corresponding pairs of sides of the old triangle and the new triangle in pairs until they meet. And here's one point where they meet. And I extend this. Here's another point where they meet. And stand down here, and here's another point where they meet. So I get 3 new points, and the theorem says that these 3 points actually lie on a straight line. And incredibly enough, they actually, within experimental error of drawing the thing, do lie in a straight line. So in fact, the theorem seems to work. It's a theorem in projective geometry. Now why do I say that? Well, it just involves points, straight lines, and incidents. So if it's a theorem of projective geometry, we ought to be able to prove it just using the methods of projective geometry. Now, these methods involve transformations of the projective plane. So before we can give a proof of this theorem, we have to study projective transformations.
Well, we've already seen that some projective transformations can be physically realized by a television camera. So let's look mathematically at what's going on there. This is a simple diagram of a television camera. And we've assumed that the lens is a point. Rays of light from the object pass in straight lines through this point to the screen at the back. Well, suppose our object is a circle. It lies in a plane, which we'll call the object plane, and the image on the screen is part of another plane, which we'll call the image plane. And the points of the 2 planes are related by straight lines which all pass through some fixed point which corresponds to the lens. On this model over here, we've got some of the lines representing the transformation drawn in. This is the domain of the transformation, this is the codomain, and to find the image of a point up here, I just draw the line through here and see where it hits the bottom plane. And that doesn't just apply to points on the circle, it applies to any point of this plane. And more than that, we're not assuming that the planes stop here where they intersect. These are mathematical planes, and they go on forever. And what we're really doing is projecting the whole of this plane through this point onto the whole of that plane. And if you do that, then by choosing the position of the planes carefully and choosing the point, then you can project a circle onto not an ellipse, but a hyperbola. Well now, you may find that a bit hard to believe. After all, how can we possibly transform a circle, which is bounded, to a hyperbola, which isn't bounded? Well, you can see how it's done in this model. You see, the circle and the hyperbola are both conic sections, and this is the cone they came from. Our object plane here cuts the cone in a circle, and the image plane cuts the cone in a hyperbola. And if I choose the point at the vertex of the cone, then I can draw straight lines joining points on the circle to points on the hyperbola. This line goes round the back, through the vertex, and down here. And a point up here would go down through the vertex and down to here, and so on. What about a point down here? Well, if I join that to the vertex and keep going, I won't hit this plane, but remember, we're supposed to be transforming the whole of this plane onto the whole of that plane. And if I add in a little bit more of the bottom plane, then you can see that by projecting the other way, I'll get to a point somewhere down here. And that's how we get the other branch of the hyperbola. What about this point here? If we join that to the vertex, then it doesn't matter how far we project in either direction, we'll never hit the bottom plane, because this line is actually parallel to the bottom plane. And so it really does look as if this point doesn't have an image. And in fact it doesn't, at least not in the ordinary plane. But remember, we're supposed to be talking about projective transformations, and we should have a projective plane and a projective plane. But everything I've said so far concerns ordinary planes. Well, at this stage we have to take account of the ideal points, and it turns out that the image of this point is an ideal point of the bottom plane. Well, the details of all this are in the text, but the message is that by using the ideal points, we really can turn this into a projective transformation from the projective plane to the projective plane.
Now, using two planes and projecting through a point gives us a very useful representation of a projective transformation. And in fact, I'm going to use that representation to prove that theorem we mentioned before. Well, this is the theorem, and it looks pretty complicated. So let's start off by trying a special case. Now, what's the most simple special case you can think of? Well, it's an equilateral triangle. So here is the special case of an equilateral triangle with a point at the center. Now, what is the construction? I extend these sides in pairs and see where they intersect. Well, by the symmetry of this case, unfortunately these sides are parallel, so they don't intersect at all. So it looks as if the theorem already breaks down in the first special case that I look at. But in fact, don't forget that we have to add on these ideal points. So this pair of parallel lines does intersect at the ideal point P. So we're saved by the projective plane. And similarly, in this case, this pair, they do intersect in the ideal point Q, and the last pair intersect in the ideal point R. So what does the theorem say? It says that these 3 points of intersection, P, Q, and R, lie in a straight line. Well, of course they do, because they lie on the ideal line. So the theorem is true in this special case of an equilateral triangle. Now, what is miraculous is that I can actually use this special case to prove the general case. And I'm going to do it by means of a projective transformation. You see, here is my special equilateral triangle, and by means of a projective transformation, I can project onto this general triangle, and this point goes to my point here. Now, the theorem is a theorem in projective geometry. It only involves straight lines, points, and so on, and therefore it must remain true under a projective transformation. It's true here, therefore it must be true here. And in fact, that constitutes a rigorous proof of the theorem. Well, there's one detail that you may be worried about. I really ought to prove that I can get from my special case to any arbitrary configuration by means of a projective transformation. In fact, that's true, and you'll see the details in your text. Well, that's an example of a theorem in projective geometry. In this program, we've introduced you to a geometry, projective geometry, which is not the geometry of Euclid. In the next geometry program, we'll introduce you to another such geometry, the famous non-Euclidean geometry.